Hi, everyone, and welcome to the AMR Narrative YouTube channel. In this episode, I interview Dr. Rodney Rohde, who, among other things, is an advisory board member of Infection Control Tips and a Regents Professor and Associate Director at the Translational Health Research Center. He's also chair of the Medical Laboratory Science Program in the College of Health Professions of Texas State University. His background is in both public health and clinical microbiology. He's won numerous awards, including being named as one of the top 20 professors of clinical laboratory science you should know. But what is microbiology? As a patient, I was really interested in understanding what goes on behind the scenes when it comes to diagnosing antimicrobial resistance, or AMR. So let's see what he has to say in his interview. So, Dr. Rohde, thank you so much for joining our YouTube channel today. It's such a pleasure to have you. I mean, we've been speaking for quite a while online, and but we've never really, spoken to each other, in person or virtually as such. So, you've done such amazing work in microbiology, and you've also spoken a lot about advocacy, patient advocacy and so on. So we really felt that you were an amazing guest to have on our YouTube channel. So, so I guess, as you know, this is a patient interview with a microbiologist. I don't know much about microbiology, and I'm hoping that you can give me some answers. So, I guess my first question is, can you tell me more as a patient what a microbiologist does? What happens behind the scenes?
Yeah, thank you, Vanessa. And thank you again for that really kind introduction. It's been a pleasure kind of getting to know you, through the internet, through online media. And it's so wonderful to finally get to kind of meet you in person online with respect to this interview. So thank you so much for this opportunity. I know you know how important this topic is, not only to yourself, but, our circle of friends and healthcare professionals that work in this area. So, yeah, so by training, I am a microbiologist. All of my degrees have primarily been in microbiology as well as public health. So sometimes I describe myself as a medical laboratory kind of microbiologist that spent many, many decades in the laboratory doing this type of work. But as you know, I've also been involved in public health. And so really the last 10 years of my career, I have, for a number of reasons, been very passionate about antimicrobial resistance, specifically MRSA, methicillin-resistant Staph aureus, because it was part of my research efforts as a professor here at Texas State University. And the reason that was part of my life was my father still deals with MRSA. He kind of gets it in bouts, it comes and goes. So we deal with that as a family. He's in his early 80s now. So for him, sometimes it even ends up like as a UTI. So it's been touch and go a couple of times. So it's obviously a dangerous type of infection. So that's kind of just some context from where I come from. And then my entire dissertation and PhD was in that world. So if I back it up a little bit to kind of talk about a microbiologist, the primary role of a microbiologist is to identify through various techniques, both manual and automated in our world in the laboratory. And for what this purpose is, it's really primarily in the world of a medical laboratory in a hospital setting. Because as people come in to a hospital with whatever ailment or illness or condition they have, typically part of what's going to happen is they're going to have a microbiological workup. And so what does that mean? That might mean that specimens are taken from a patient, like sputum or a urine culture or blood, or even a swab of their throat or a wound. And so that is typically done at the front end, per se, that specimen intake. And then that specimen comes into the laboratory where people like me and other medical laboratory professionals are going to work it up, right? And what does that mean? That means they take that specimen, and based on the physician's assumptions and suspicions of what's going on, they're going to take that and they're going to plate it. So they're going to put it on a petri dish. that is a way to grow and culture. We'll use the term culture bacteria and to grow it up. Let's stop here for a moment, though, Vanessa, because we tend to focus on bacterial infections in the world of antibiotic resistance. But let's remember that there are many other pathogens. So there's also fungal resistance, there is a viral resistance, there's even protozoal resistance like malaria. So there's classes of organisms, just like there's classes of plants, classes of animals, however you want to kind of think about that. And really that's our job, is we need to identify it. That's number one. What is it? And then right after that, as you know, the next most important test in the realm of AMR is a susceptibility test. Which drug, which antibiotic, which antiviral, whatever organism you're looking at, which drug is going to effectively eliminate that infection? The fastest, the safest, and the most effective way of saving that person's life, perhaps. So those are kind of really the core of things that we do. Now, there's a lot of other testing we do with respect to different types of answers for different things. But the primary role for us is to identify the organism, the pathogen causing the infection, and then doing some type of testing. Typically, we refer to that as antimicrobial susceptibility testing to find out which drug is going to reduce or kill it so that the person can recover from that infection.
Wow, you know what I mean? These are this is information that I felt, when I was a patient trying to overcome MRSA or MRSA, as some people pronounce it. That would have probably made a huge difference to me. I guess it leads me on to my other question, because when I got MRSA, MRSA, and when I learned that it was antibiotic resistance, I had never heard of this before.
Right.
And that really concerned me, that it wasn't common knowledge. So as a microbiologist, to a non-scientist, to a patient like me, how would you describe what antimicrobial resistance, or AMR, is?
Yeah, great. Right. That's the core of why we're talking today. It is so important. It is so important to patients, as well as what I always call their patient advocates. As you know, it's really important, if possible, to have those around you, your loved ones, family members, friends, because sometimes the patient, as you know, in your experience, may not be able to understand what's happening because of the state of the condition. They may be septic, it may be life threatening, and you might need others. So I'm a big proponent of, as you are, patients have to kind of get a grasp of this, but so do other people in society, because you never know. Like I'm my father's advocate. Sometimes he is literally out of it. Like if he's going into early sepsis or something, he's confused, he's disoriented, and so just want to make that point that it's not just a one person type of understanding, it's those around you. So if you have a problem, especially if you've had bouts of AMR, take some time to make sure your family and loved ones and friends understand it as well, because they may be there by your side in an emergency. And before I jump into what it is, it made me think of you when you said that about undergoing it. If you would have understood it a little bit. For me, when I was a brand new college student in university, when I took my first microbiology course, what really grabbed me was how beautiful these things are. That may sound strange, but you can't see a microbe with your naked eye, at least as an individual organism. You have to use microscopy. And so I'll never forget, as a sophomore, about 19 years old, taking my first microbiology course of making a gram stain, which is the way you stain bacteria, on a slide, dropping it on a microscope, and you have to bring that up to 1,000x to actually see the little circles like grape-like clusters, like MRSA, like Staph aureus, or those pictures you might have seen on TV or in a magazine image. You can't see that with your eyes. So patients have no idea what's in their body. And so it's both beautiful and frightening, because sometimes when you see those things on a slide, you might be really intrigued at just the artistry of it. I mean, they really are interesting things to look at, as well as fungi and things like that, but they are deadly in many instances. So just kind of a contrast in how that microbial invisible world is something that most people never see without the background in a laboratory setting. But what AMR is, and let's be specific for the audience here, that stands for antimicrobial resistance. It really crosses all spectrums of pathogens. So we could talk about antiviral resistance or antifungal. Let's focus for a minute on bacteria, because that's really kind of one of the primary players in AMR. Typically what happens, it's a really complex problem, as you know, and yet it's simple. So bacteria have the diabolical property of rapid reproduction. They can reproduce about every 15 to 20 minutes, and they do this 1 to 2 to 4 to 8 to 16 to 32. They double. It's called doubling. And as they do that, they have the ability to mutate, and they do it naturally. So you might think of that as evolving or adaptability, kind of in a different word. They respond to certain things kind of in a normal, natural way. This happens, across most organismal worlds, because that allows you to become stronger and adapt to the surroundings. Unfortunately, with bacteria and other organisms as well, when we misuse antibiotics, for example, we take them through self prescription, like we have leftover antibiotics and we just take them on our own because we think we know what we have, or when we might see them in the animal setting. They're often given in vast amounts for livestock to keep livestock healthy. That can run off into the environment, into water. So it's all around us. It really is. So it's a really complex problem, and it's different in different parts of the world due to regulatory differences. And in some places in the world, you and I could walk right into a pharmacy and buy whatever antibiotic we want. That's kind of dangerous because there's no oversight of, do you even need it, right? And so that's a problem. And so when you have that constant exposure, when the bacteria is constantly being bombarded by antibiotics all around it, whether it's in the body, the environment, in whatever kind of aspect you want to think about it, it undergoes something called selective pressure. Now, what does that mean? That just means that it's going to evolve and mutate like it's on steroids, for lack of a better way to describe it. It's rapid. It's sometimes multiple mutations where it might be resistant to multiple antibiotics. And so you end up with these things, as you know, called multiple drug resistant organisms. So it's not one drug. They actually don't respond to multiple drugs, and sometimes entire classes of drugs. And so ultimately what that means to the patient is that if you acquire one of those resistant infections, that testing is even more critical, because the physician and the laboratorian and the healthcare team needs to know that you have MRSA versus regular Staph aureus that might be treatable pretty simply, right? I mean, 50 years ago, you had a staph infection, you took penicillin, you were good to go. Unfortunately, that's not true every time now. You might have Staph aureus that's methicillin resistant, or worse, vancomycin resistant, or something else. So, and we're just picking on MRSA. There's so many acronyms that we could throw out here. There's a multitude, like TB, tuberculosis is highly resistant, and it goes on and on and on. And so it's really critical for that laboratory test to take place in a very accurate way, in a very rapid way, as much as possible, so that the right drug and the right healthcare kind of program can be initiated to get you cleared of that infection very rapidly. Because sometimes if it's sepsis, if you get it in your blood, it can be very deadly. So this happens a lot, right? And we could talk a little bit more about that maybe as we go forward, but there's other problems because bacteria can talk to each other. So if you imagine these are two bacterial cells, they have these fine hair-like structures called pili. They're like tentacles of an octopus kind of sticking out. They can touch and horizontally transfer what's called a plasmid, which carries a resistance factor to methicillin. So let me slow down a little bit, right? So it's a little technical, but that means, Vanessa, that if we could touch, like if I could touch you with your finger like that, that I could give you gray hair horizontal. I could
Mm.
have you that mutation happen instantaneously almost instead of through the reproduction route, which usually takes longer or age. So if you can imagine bacteria just touching in a human body or on a surface, wherever, and transitioning that resistance characteristic over, then it's immediate. And so that's a whole nother problem with respect to mixed infections and what happens when you don't isolate patients. You can actually create more problems. So again, this is a really complex topic that, you know, sometimes people have a hard time getting their head around, but it's so critical that if you take nothing else from this talk, that you have a really appropriate test run and the identification of that bug alongside a susceptibility test. That is the core essential information, so that if you're ever in that situation, someone can ask, why aren't you running a test? Why are you just giving me a prescription for something? I need to know. You need to know what the infection is so that you get the right drug to treat it.
I guess that, I mean, we had a couple of questions that we had highlighted, and I'm going to skip towards the end of those because I think you've answered a lot of them, which is amazing. Really, really, it's educating me as somebody that, again, I've worked as a patient advocate, but I don't have a scientific background. So, it's helping me really grasp the topic.
Yeah.
I think one question I still want to ask you is, I'll probably combine these. So, what sort of diagnostic tests are used right now to identify AMR, and how do you think we can improve these diagnostic tests in future, and why does it matter to patients?
Yeah, this is a great question to move forward to, because this is kind of in the core area of diagnostics and how critical that piece plays in the identification, as we mentioned. So let's remind people, you need to know the bug, you need to know the pathogens that's causing the infection. And then right next to that, just as important, is which drugs are most effective against that particular pathogen. So, historically, what we've done in the medical microlaboratory is we have grown bacteria up on a culture plate on a petri dish, and there are so many ways that we really don't have a ton of time to go into, but there's so many ways to stain them, like a gram stain, to identify kind of a broader group. Is it a gram negative or gram positive rod? That helps break them out into kind of buckets. And we're just talking about bacteria here, because there's other tests for fungi and stuff, but gram negative or gram positive, what they look like. Are they spheres like staph? Are they rods like E. coli? Are they spirals like Vibrio? And so there's just a ton of kind of understanding from a microbiologist perspective of kind of that top level suspicion. And then we move into more semi or automated types of technology where we grow them up on different types of media that will be selective. So there's entire groups of bacterial media. When I say media, I mean bacteria can grow on top of different types of media on a plate. It's all sterile. And so you can select, like I have media that will select for MRSA, which is wonderful because remember, bacteria in the human body sometimes is in a pool, dozens and dozens of normal bacteria that are on your skin or in your gut. And so you need some way to, I always say, fish them out. It's one way I talk to the public about it. You need the right hook, the right bait, and you're fishing out MRSA, for example, on this plate. And so once you have that, then you move into a susceptibility test. Now, in the old days, susceptibility test was done by putting antibiotic disc, penicillin, vancomycin, Cipro, whatever it is, actually on the top of a plate. And this is where I wished I had a plate to show you. Perhaps you can show that later.
Yeah, we
And
will.
so
Yeah.
you would look for, can the bacteria grow up next to that disc? And so in a simplistic way, if it couldn't, if there was a big zone around that disc, then you knew that that the antibiotic was working. It was actually killing off the bacteria because it couldn't get close to it. If it grew right up to it, then it's resistant. And this is kind of simplistic because there's all levels of of how you do that. You measure it, there's tables, there's standards, and all this was basically manually done. Now you can already see the headache in this, right? It takes time. So to do that type of work, you could be looking at 24, 48, maybe even 72 hours for most common pathogens. Now, some are pesky. We call them fastidious. It could be longer. It could be a week. And certainly if you're septic, game over maybe for the patient. You can't be waiting forever. But that's what we had for many decades. And then we moved into an automated system where, if you can imagine, you can grow up the bacteria in a very pure way and literally put them into, they look like credit cards. And if you could imagine on a credit card, little wells throughout that credit card that might have 60 different biochemical tests. And it gets loaded in the machine. It watches their growth and color changes and different types of things that those little slots have. And it would identify that bacteria maybe in 6, 8 hours. A great improvement. And right alongside that, in another card, so you'd have another card called a susceptibility card or an ID card. It had maybe 60, 80 antibiotics. And by way of growth or no growth, the machine is recording it based on turbidity. Is it growing or not? You could also get a profile for which antibiotics were the best to use. Again, huge improvement. So again, sometimes definitely within a day and sometimes within 6, 12 hours, the physician could be giving you the appropriate narrow spectrum drug that's going to target that bug like a rifle, instead of guessing with a broad spectrum drug that might do the job, might not. And that's a whole nother topic, narrow versus broad spectrum drugs, because broad spectrums, you might have to use it in an emergency like sepsis, because they just have to treat, like in an emergency room situation, you're going septic, you've got a bloodstream infection, you're going to die. And so sometimes the physician has to prescribe an antibiotic without testing. And you hope that big broad spectrum kind of shotgun effect will get the bug. And usually it will, right? We have really good broad spectrum drugs. The danger with that is that you're also setting up resistance with other bugs. That's kind of another topic. You really want to use a narrow spectrum drug to kill some. So that's still done. There's many different automated devices that do this, and we won't mention manufacturers, but they're all over the world. They work pretty well in that standpoint. But where we're headed, since you asked that question, excitingly, there's testing called MALDI-TOF. There are other molecular-based tests that look at nucleic acids and are getting to the point where we're hoping that we're going to get to the point of care type of test, which could be almost immediate. And by immediate, I mean several hours, maybe 2 to 4 hours.
Wow.
I was digging around yesterday when I knew this was coming, because this changes so rapidly in the diagnostic world. But there are many papers being published right now that do this. They're looking at trials where there's some really positive data coming out within 2 hours of identifying that organism. Now, most of the world knows about, after COVID, after the pandemic, how rapidly PCR-based, molecular-based technology can be, how powerful it is. And so they're just going through the processes of validation and trials and kind of looking at that. And there's always new platforms and new manufacturers to kind of think that way. But the hope, Vanessa, is that one day, as you kind of mentioned, maybe there will be a bedside test that even can give us information within 2 hours. And you can imagine how many lives can be saved if that type of test is available. We have to make sure it's accurate. We have to validate it. But that would be the next generation of testing that would take it from 6 to 12 hours down to 2, maybe even less. Even if it's just for, the way this works sometimes is they may make sure it works for the top 10 dangerous bugs, and then we keep testing for more expansion of kind of intermediate danger and things like that. But if we could get it to help us with the top 10 or dozen organisms that are multi-drug resistant, you could save countless lives. And anytime you have accurate identification and better drug prescription for the right bug, you also start reducing the problem of AMR kind of on a bigger scale. So diagnostics and diagnostic stewardship, which is selecting the right test for the right organism and things like that, is critical. And I'm going to point the finger kind of back at us because we're a critical part of that world. So the medical laboratory, clinical microbiology, alongside physicians and ID pharmacists and infection preventionists and others that are in this game together, that team approach is so critical because that's what we do. We do testing really well, and so you need that communication and that education between all those players, just like patients need to understand some of this. So it's exciting. It's exciting to think that laboratory testing could help lead the way with some of that earlier identification. We still have to work on all those other things, the misuse, the use of antibiotics and livestock that's out of control or food production. There's all these problems, but you've got to start in every place. Mm-hmm. And it's, as you know, it's kind of hard, right, for I think the world to think about, but we have to start and keep sustaining that effort so that we can at least start reducing AMR globally.
I guess you've answered all my questions then, as a patient and, very eloquently as well, because, like I said to you, it's not easy for us to kind of, get, as I said, what goes on behind the scenes. So I really appreciate your time. And for, being on our YouTube channel and for making it a little bit more understandable for us as patients to know, what the role of diagnostics are. And again, is the role of a microbiologist and how important you are to tackling AMR. So thank you for being here with us.
Thank you, Vanessa. And I'm going to throw it back at you. I'm so grateful for patient advocates like you that are willing to be honest and share your story. Transparency is critical in any true problem, whether it's political, medical, or whatever. I mean, transparency really helps shine the light on the danger. And sometimes the danger is miscommunication. The science might be there, the medicine might be there, but if we can't get people to be transparent and learn from our mistakes and how we communicate things, then we're going to spin our wheels. So I'm just really thankful for you and for others like you. We know there's many like you out there that have a voice. And I would encourage, if you're watching this video in the future, to share your voice with Vanessa and others so that we can impact even more people around the world. So thank you.